So how enthusiastic are you for the new chapter? Remember, we are going to do completely new chapter today. This is completely new. You have never studied this in your grade 9, 10th, 11. This is completely new. You have studied reflection, refraction, but that was all ray optics, not wave optics. Which? So wave optics, Ninad, we are talking about the wave optics today. Yeah, wave nature of light. Vasudev is asking about the weightage. A lot of questions are asked on interference, Young's double slit experiment, numerical section especially. So you have to do the numericals of those. So many questions are based of that, interference, diffraction. So you got to focus on this chapter especially. Okay. Any questions, any doubts? So then today's agenda is wave optics, and this beautiful pattern that you might have seen in the soap bubble is thin film interference, by the way. This is interference. So let me start by understanding how much you know about light. So Ninad, you have been writing what, like couple of times, what is your question? You're writing what, 3 question marks, what, 3 question marks. So what is your question? What are you asking? So be more specific. I'm waiting for your. What is that image? That is a soap bubble. You blow bubbles, right? Like take a soap bubble. So, right. So do you have you noticed, like even in the CD, like CD, like compact disc, you might have seen the colorful pattern there, right? So these colors, these are like thin film interference. That is part of your curriculum. So we will study that. Okay. So tell me, what is light? I'm just trying to understand how much students know what is light. The answer, it is dual nature, right? We have covered this in the previous chapter itself. Electromagnetic radiations have dual nature, wave nature and particle nature, right? So I was hoping everybody is going to give the right answer there. Now, which phenomenon cannot be can only be explained by wave nature? If you have studied this, tell me. That's fine. Don't make a guess here. I'm just trying to understand how many of you have already studied this. So which phenomenon can only be explained by wave nature? Interference, photoelectric effect. And if these terms are like not making sense, like interference, diffraction, we are going to cover them from the very beginning. Wave nature fails to explain photoelectric effect, by the way. I have spent so much of time explaining photoelectric effect, and I said wave theory fails to explain that, and you're saying wave theory can explain photoelectric effect. 29% students are saying that. Yeah, Rukaya, you're right. Interference can only be explained by this, right? So don't worry, we're going to start from the very beginning. Yeah, Nina read the question wrong, and that's not what you should do. You should read it properly. Okay. So let's get started with the understanding of what is light, first of all. Okay. What is light? As we said, it has a dual nature. And I gave you a brief history. I'm going to start with that history now because we are going to study more on what thing can be explained by wave nature, what can be explained by particle nature, and so forth. So Newton proposed, first of all, the corpuscles theory or the particle nature. Mr. Newton said it's particles. The light is particle, right? So you were able to understand what is reflection here. Check, right? You can explain a reflection. Newton was able to explain what is a reflection based on like how reflection works using the particle nature. He was also able to explain like refraction. Those were most of the things that were known at that time. You could see a mirror, you could see water refracting the light, the bending of light and all that, right? But then came more experiments like interference. So when you study interference, what is interference? Interference is when two waves meet. We are going to do this in detail. Maybe more than 1 hour or 1.5 hours will be dedicated to understanding what is interference. And then we'll spend another hour or maybe less than that in understanding what is diffraction. So diffraction and interference are when two waves meet, what is the pattern formed there? And this is only when two waves meet. And light shows interference and diffraction. And this is when Young and more important like Maxwell, those kind of people, they came up with the theory saying light is actually a wave now. Light is not a particle, it's a wave, because if it is a wave, only then you can explain how light is showing the interference and diffraction. But then you can also explain things like reflection, right, and the refraction with this. So you're able to explain reflection and refraction as soon as you say it is wave, but then you can also explain interference and diffraction. So now the problem is solved why it is showing interference and diffraction, because it is a wave. But one thing that remains unexplained is uh, photoelectric effect. Electric, okay, and Crompton effect. So these things cannot be explained using the wave nature of light. Okay, and then came Mr. Einstein. So you really have to know this history in order to understand what is light actually made up of. So Einstein proposed that it is both. So as soon as you say both, you can explain everything. You can explain interference, diffraction, reflection, refraction, photoelectric, and Crompton. So he is proposing it has a dual nature. So light is both particle and wave. So this is a big breakthrough. I mean, this is what Einstein got the Nobel Prize for. He was able to explain light as being both, and now you can explain why photoelectric effect happens. Okay, thank you, Ninad. Ninad is saying the audio is not clear because of the fan here. So let me turn off or maybe slow down the fan. Actually, the point is the weather here does not permit me putting on the AC. I'm sure I'll have a very bad throat if I turn on the AC. It's raining, so I have to rely on the fan here. Ninad, is that better now? Ninad, is it better? Please say yes or no fast. Okay, that's good. Thank you for that. I'll be sweating here, but at least my throat will be better, right? So yeah. So Einstein said it is both, and this is why he got a Nobel Prize. Now, um, right, and then this was taken further by saying dual. So this is dual nature of radiations, right? And then we are proposing dual nature of matter. Matter is also dual nature, right? So this phone is a particle and it is also a wave, right? So this is the history we already covered in the previous sessions, but then see some students were not still clear because I didn't get 100% answers. So light is both a dual nature. Now, what you studied in grade 10th, so what you studied in grade 10th was more like ray optics, right? So what is ray optics? Ray optics is you draw the rays of light and then say, oh, there is a mirror here and the ray comes back, right? This is what you have studied in grade 10th, ray optics. You draw rays. But what is a ray? Right? We are saying light is a wave or a particle. We are not saying light is a ray, right? So ray can be assumed as the path of travel of the light. You can assume that this wave is traveling in this direction. Or you can say, no, actually it's not wave, it is photons traveling in this direction. Right? So you're isolating all that. You're saying, okay, I don't care whether it is light is a wave or a particle, it is traveling in this direction. So ray actually tells you the path of travel of light. Right? Behind the scenes, you have to think about whether it is this ray is made up of photons or it is actually the path of travel of the wave. Right? So that is what we study. Now we will still study ray optics today. Not today, I mean in a few weeks from now. Today we are focusing more on waves. We are going to see how light is actually a wave. Right? So it is electromagnetic radiations, as we already saw. There is a fluctuating electric field, right? This is fluctuating electric field, and that makes up a fluctuating magnetic field. So this field, green color, is coming out of the whiteboard and going in. It's in the XZ plane. And together, these two fields, fluctuating magnetic and electric field, they travel in this direction with the speed of light, because this is light, right? So this is what electromagnetic radiations are made up of. Now, depending on frequency and the wavelength, it can be visible or non-visible. So we can look at it as VIBGYOR, that human eyes can see, but then we also look at infrared, radio waves, microwaves, and then on the other side is ultraviolet. Then you have X-rays and gamma radiations. Now, when we are talking of wave nature of light or whatever, we are talking of the entire family. Even though we are limited to seeing only VIBGYOR, but everything what we study in wave nature or photon nature or ray nature, everything applies to all the members of this family. So even though we are going to do Young's double slit experiment by using one of the wavelengths here, but you can do the same thing with any of the radiations here. The setup will be a little different. When we do the calculation of the size of the slit and all that, everything will change depending on what light portion you're talking about. So from here, any confusions, any doubts, any doubts? I'm pausing here. Please take the opportunity here. We have 4 classes dedicated to wave nature. We have enough time. So don't worry about the time management. We have enough time. In fact, we are ahead of the schedule. We finished modern physics a little earlier, so we can do revision if required. ठीक है, ठीक है. Vasudeva, your point is definitely right. Normal to wavefront, and that's what we are going to cover in few minutes from now. Yes, Vasudeva, that's really good. Okay. So now let's use the slides here. So introduction to wave optics. Okay, so some kind of history. I did a better job by putting everything on one page. This is talking about the same thing. What is light? It was bothering physicists for a long time. Just go through this. And as we already did a very brief introduction to relativity, we saw light is special, right? It's the only thing that can travel with 3 times 10 to the power 8. And it is the only thing which has an absolute number. 3 times 10 to the power 8 is an absolute number. It doesn't change with, it's not a relative kind of thinking. It's absolute. More students have arrived, Rhythm has arrived, and many students here so far. Yeah, thank you everybody for joining. Any doubts, any questions you can ask me. So I'm showing the slides of whatever I covered already. Okay. So 2 major theories, as we said. So Mr. Newton started by saying it's packets of particles, and then Huygens and Maxwell took it further, and it actually started with Young's double slit experiment, that light shows an interference pattern, and we'll see what that is, right? And then it was assumed that Newton made a mistake there, light is actually wave. And then, but then you could not explain everything. And that's when Mr. Einstein jumped in and he said, it's actually both. And that was a big statement to make. Okay, there's some things we already covered. These are the things we have already covered. So when you look at the light reflecting off the mirror, you can think of light being particles or you think being waves, doesn't matter. Both the ways you can explain it. This is not a problem at all. Any of the theories will work. Same thing goes on with refraction of light. You can take any of the behavior there. You can equally easily explain the behavior of why light bends. Right? No problem with that. And that's what it is saying. This can be explained by particles or assuming it is wave. Doesn't really matter. That's not a problem at all. Now, there are few phenomena that you could not explain using particle nature, like interference only can be explained when you think of light as wave. Particles will not be able to have interference. Two particles never interfere. Waves interfere. Same thing with diffraction. Diffraction of light is, yeah, we'll see that. Bending of light around the corner, we'll see that. Right? So that cannot be explained using particle nature. Similarly, polarization. Polarization is something like, I don't know how many of you are in photography, like the real photography, not the one with your cell phones, like the real photography, as in you use the filters and all that. So if you have ever used the circular polarizer to make your sky look more blue, or cut off the reflection. I'm a lot into photography. I have like maybe a big collection of photography books here, and I have big collection. Yeah, Ninad is saying sunglasses, polarizing sunglasses. So that polarization effect cannot be explained assuming why is light polarized. Polarization is only a phenomenon associated with some kind of wave. So particle nature is not being successful here, right? On the other hand, photoelectric effect and Crompton effect also, let me write it here. Crompton effect is not in your curriculum actually, but I'll introduce it. It's like 2-minute thingy. So again, this fails and particles pass there. So these are the two phenomena that could not be explained using wave nature. And this is where Einstein jumped in. Okay. Any doubts you don't have to wait for me to ask, you can ask me anytime. Now wavefronts is a new concept here and Vasudeva seems to have understood it already because Vasudeva, yeah, gave me something. Yeah. Okay. So let's go through this. What is a wavefront? तो wavefront क्या है? Like look at the ripples here. Maybe I'll zoom in. I'll try to zoom in. I'll try my best. Okay, ripples. Look at the ripples here. Ripples, when you drop a pebble there, you see the kind of circular thing there, right? So if you look at one of the circles there, aren't these the particles going together up and coming together down? They're in the same phase. So let's actually not do this. Let's draw our own. So let's say this is a pond and you drop a pebble. You will see this pattern here. You will see that these particles all on this circular rim, they go down together, they go come up together, they are in the same phase. So this is one wavefront. Another wavefront. All the particles in the same phase. It's a locus of the particles in the same phase. That's it. So they all go up together, they all come down together. So this is a wave front. Has everybody understood, or is it like confusing? If you don't understand this, let me know right now in the chat box, please. Is okay, let me ask a poll then. People hesitate. So is wavefront clear, true or false? Clear, true, not clear, false. All the particles going up and down together in the same phase. They form a wavefront. So this is one wavefront, this is second wavefront, and you will have lots of wavefronts here. All these particles, they go together up and come together down. So that is a wavefront. Okay, I will repeat one more time. Couple of students are saying repeat it. So let's repeat it. So it's a locus of all the points going up and down together. So it's more like the wavefront. So I'll draw it again here. So let's say that you drop a pebble here, and then all the particles here, they go up and down together. And then another wavefront here, all the particles on this one go up and down together, right? So all the particles on the blue one go up and down together, right? So this is called a wavefront. Oh, screen isn't visible, sorry. Okay, my bad. Sorry. Okay, this is the result I saw. Like 7% students said could not understand. Couple of them wrote it on the chat box that please revise. So that, sorry. So if this is the dot here, this is where you drop the stone or the pebble, you will see the waves going outwards, right? So all these particles, they're going up and down together. See, wave is traveling, the particles don't travel, right? That's how the waves work. So they just go up and down together, and these ones go up and down together. These ones go up and down together. This is called a wave front. Is that clear now? Okay. Now, if you look at this, isn't the wave traveling in this direction? Right, it's traveling this way. Right, wave is traveling in this direction. These are the rays of light. This is what we talk of when we talk of rays of light. Yeah, but in all directions. So it's like you have a point source of light, maybe a bulb here. It sends out the light in all directions, doesn't it? A point source of light. You're right, in all directions, like Ninad is saying. Right, so it sends out the rays in all directions. Clear so far? Clear to everybody? Please tell me. If not clear, I'll explain again. Okay. Now let's look at it from another perspective, or maybe I'll draw longer lines here. Then you will understand better. 1 second. So I'm saying that this is the source of light, maybe green light. No, red particles go up and down together, black go up and down together, blue go up and down together. Because see, when red was going up and down, blue was not even started, right? So blue has a different kind of starting time itself. Right, so let's say these are the two rays of light, let's say. Just two rays of light is what I'm going to draw. Just to illustrate. Two rays of light. Okay. Now, if you look at here in this zone, you can see the rays of light are like kind of diverging. Aren't they diverging? But now if you look in this area, let's say I hide everything from you. I don't even show everything. Don't you think these two lines, line number 1 and line number 2, they look more like parallel lines to you? Please look carefully. When you go far away, the lines actually look more like parallel lines, even though they are not parallel lines, but they look like parallel lines. Does everybody agree to that? Please say yes or no. right? And this is why when we say the light comes from a far source, the rays of light come parallel to each other. This is why you say that. The further you go, the curvature there will be gone. You don't even realize there is a curvature. Now if you look at from this perspective, let's say you're talking from this perspective, if you chop a piece here of 1 centimeter, it is very much curved. But then if you go far away and the circle is more like this, let's say the circle, something is wrong there, 1 second. Yeah, this happens if I click on discussion there, something happens. Oh no, no, wait. Yeah, there's a problem with the whiteboard there. Yeah. So now if you go far away, your circle is more like this. And if you look at this, this is a plane wavefront. The curvature is gone. The circle is so big now. It's more like you're standing on the ground here. You know the earth is round, right? But you look at the floor of the room, doesn't it look like a plane now? The bigger the circle, the plane thing it looks like, right? The curvature is gone. Does everybody agree to what I'm saying? I'm saying when you go far away, two things happen. First of all, if you're looking at the rays, they become parallel. Rays are parallel. They look like parallel. Number two, if you look at the wavefront, so wavefront becomes flat. There is no curvature at all. So the farther you are, the more the flatness in there. Does everybody agree? Then I'll move on to the next slide. Right, far away, two things. First of all, rays look like parallel and the wavefront looks like a flat wavefront. There is no curvature because all that curvature is gone. It looks like a flat thing.